Welcome back. We've been talking about the proximal gradient method and showing that in settings where we have composite optimization, the proximal gradient essentially gets us as much benefit as we could hope. In other words, we get the same rates of convergence as we did just for gradient descent, even when we had smooth functions. So after all of the analysis that we've done, now we're going to see it in action in the two probably best known instantiations of proximal gradient, the algorithms affectionately known as ISTA and FISTA. ISTA stands for iterative, shrinkage, and thresholding algorithm, and FISTA is creatively named just the fast FISTA. So let's just review the basics here. So we're looking at problems that have the following form. They're called composite. We want to minimize a function f of x that has some particular structure. It's equal to g of x plus h of x, where g of x is smooth, and h of x has, in quotes here, an easy prox operator. We'll remember again what these mean when we see them in a particular example. But everything here is convex. So f is again convex. So just in the way of review, if we have a convex function, whether or not it's smooth, we can always use the subgradient method, which we've seen in previous lectures. The subgradient method tells me that I should update x as follows. xt plus 1 is equal to xt minus my step size times some element here. Oops, I think this is overloading notation a bit, but this is a pretty standard notation, so hopefully it'll be clear. Minus gt, where gt is some element of the subdifferential of f at xt. This is a subgradient method, and I could just apply it directly to f. And if h is not smooth, as it typically isn't, then we can't really take advantage of the smoothness of g of x. And so we have to use a subgradient method if we want to apply it directly to f, and this would give us convergence order 1 over square root of t, which means that in order to get epsilon error, this is the same as saying that I need 1 over epsilon squared iterations of this algorithm in order to have error epsilon. But we saw in previous lectures that we could also try to use the proximal gradient method. So proximal gradient tells me that xt plus 1 is equal to, and now let's see what I want to do here. G of x is smooth, and I want to take advantage of that smoothness. And you'll recall that the way we take advantage of smoothness is that we don't need to have our step size going to 0 or being linked somehow to the final error that we want. We have what we've called the self-tuning property. So I'd like to take advantage of this, and here I hope it's going to be a little bit clear, even though I'm overusing my notation. Here I'm actually speaking of the gradient of the function g at xt, whereas before I was using g for subgradient, just because that's notation that we've used before. Okay, but obviously this can't be it, because there's something missing here. I haven't captured anything of h, and indeed what's missing is the prox operator applied to this. So this is saying here prox with step size eta of the function h of the step size of the gradient. And this has convergence, as we showed in previous lecture, order 1 over t. Unless, of course, g is also strongly convex, and we showed that we get even faster convergence, but we're not going to think about that for the time being. Which is the same as writing that I need 1 over epsilon, right? So the third element that we're going to talk about, so this is going to be ISTA. The third element that we're going to talk about is proximal gradient plus acceleration or momentum, which we've talked about before. And in this case, and I'll write down in the next slides exactly what this algorithm is, but we're going to get even faster convergence. Our convergence in this case is going to be order 1 over t squared, which is the same as saying that in order to get epsilon error, I need to make 1 over square root of epsilon steps. So you can see that FISTA, fast ISTA, is much faster than ISTA, which in turn is much faster than just the subgradient method. Okay, so I'm going to talk about in the next slides exactly what FISTA is and how we would apply it. But also I'll talk about them in the context of probably the most popular place where they're used. And this is for the so-called lasso or L1 regularized regression problem, which we've also seen before. So what is lasso all about? The idea here is that there is some vector, very high dimensional, x. I'm going to write this in RP, and you should think about P as being very large, which we wish to recover. So in real applications, X is often something like an image. In particular, lasso has been used with great success in medical imaging. And the point is that we don't have direct access to X. We can take linear measurements of it, or possibly even noisy linear measurements of it. So in other words, we see X only through noisy linear measurements. In other words, what we see is at the ith measurement, it gives us yi, which is equal to a vector ai times this unknown x plus some noise. So this is our typical model. Okay, so epsilon I is noise. So we could ask generically, how many measurements do we need? How many measurements do we need? And well, the generic answer is if I have a p-dimensional vector and I'm making linear measurements, then I need one measurement, in other words, one equation for each unknown, and possibly a little bit more because I have noise. So typically we'd expect, if we have no further information, we need n measurements, where n is bigger than p. Ideally, the bigger than the more it is, much bigger it is in p, the better. But the idea with lasso, which comes from the motivation that stems from a lot of these medical imaging applications and other applications as well, is the setting where we happen to know something about x. And what we know about x is not linear information, it's nonlinear. So the additional story here is that suppose that we know in addition that x has only a few non-zeros. So let's suppose that x, our unknown vector, has only s non-zeros. And we don't know which ones are zeros and which ones are zero. If we did, we could just eliminate all the other variables and then we would have a problem with a much, much smaller p. So the point is that even if s is equal to 1, even if there's only one non-zero, there are still p unknowns. We don't know any of the elements of x. Any one of them could be non-zero, even if we know that it's only one. So this s is sometimes referred to as the sparsity. And the key point here is that in many applications, the natural signal is sparse in a particular basis. either sparse or near sparse. So suppose X has only S non-zeros, perhaps we can get away with fewer measurements. And there's been a considerable amount of theory and analysis of when we can recover such a signal. And that's not what this class is about. But if you want to read more about it, you should read about compressive or sometimes compressed sensing, or sparse regression. There's quite a huge literature. But here we're interested in just purely the optimization story. So one of the most popular algorithms for recovering a sparse signal is called lasso, or L1 regularized regression, which is exactly what it sounds like, and in fact we've seen this in past lectures. So let me just write here the punchline that under some technical assumptions, it turns out that we need way fewer than p measurements. It turns out that if we have n is something like the sparsity times the logarithm of p. Again, there's some constants here. Then this is plenty. In fact, if it's this divided by epsilon squared, then this is enough to get error epsilon. Okay, but again, this is not what this class is about. It's not about analyzing this. So under these technical assumptions, with this number of samples, the following algorithm succeeds. And understanding this algorithm and how we solve this optimization is what we really care about. We set X to be the argmin of the following problem. Not just the standard regression problem, this would be ordinary least squares regression, but regularized by the L1 norm, where remember that the L1 norm is the sum from I equals 1 to p, because X has p variables, of the absolute value of xi. Okay, so now let's look at this objective. It's certainly convex. It's a sum of two convex terms. And the first term is smooth. It's not going to be strongly convex because n is less than p. But the second term is not smooth. So overall, this is convex but not smooth. So of course, I could just apply subgradient descent. So what would subgradient descent? Let's remind ourselves what this algorithm actually does. So subgradient descent would initialize at some x0, and then at time t, it would update by setting xt plus 1 is equal to xt minus the step size times something in the subdifferential of this function. So I've made a mistake here. This should be, of course, y. The subdifferential of this function looks like twice times A transpose times AXT minus y. That's the derivative of the first part, plus something in the subdifferential of the second. Remember that subdifferentials are exactly like derivatives. So the subdifferential of the sum of two terms is just the sum of the two. So the subdifferential now, an element of the subdifferential of the L1 norm is lambda times z, where z is anything of the form zi is equal to plus 1 if xt, if the ith coordinate of xt is positive. It's equal to minus 1 if xt is negative. In other words, it's just equal to the sign of xt if it's non-zero. And then it's any element in minus 1, 1 if the ith element of xt is exactly equal to 0. So this is a subdifferential. And if I use this algorithm, then this guarantees me, as we said on the previous slide, order 1 over square root of t convergence, which again is the same as order 1 over epsilon squared convergence. So we want to do better than this. And what motivates us to do better is that looking at this term right here, we see that this is the sum. It's indeed a composite function. So this is smooth, and this has an easy prox, as we've seen before, and I'll remind you in the next slide. So we want to do better than subgradient descent. What does proximal gradient tell us to do here? So again, what do we have? The generic setting is I want to minimize my f of x, which is equal to my smooth term, g of x, plus h of x. For us, this equals ax minus y squared plus lambda times the L1 norm of x. Proximal gradient tells me then that xt plus 1 equals prox eta times h of xt minus eta gradient g of xt. So to make sure that you've pulled together everything that we've done so far, you should ask yourselves and answer, though I'll do it for you in a second, what is eta? What should eta be here? So if you want to pause just to think about this for a second. So remember that eta is going to be what we need in order to take advantage of just the smoothness of G. So the right choice of eta here is 1 over beta, where G is beta smooth. Remember, that means that the gradient of G is Lipschitz with Lipschitz constant beta. Not just that the function G is Lipschitz, but its gradient is Lipschitz. And therefore, what is xt plus 1? I'm going to write out what this prox operator means. So by the definition of the prox operator, which we saw in the previous lecture, this means that xt plus 1 is the argument of h, lambda x, so this is a min over x, plus 1 over 2 eta. But eta is 1 over beta, so that turns into beta over 2, times x minus wherever I evaluate my prox. In this case, this term here, I'm making it kind of clear because the notation gets intense, goes here. So x minus xt minus eta gradient, and this is the same eta, so I should just write 1 over beta here, times the gradient of G evaluated at xt. This is the 2 norm squared. This is just the very definition of prox. And you'll see that this is exactly equal to argmin x of lambda divided by beta times x plus 1/2 x minus xt minus 1 over beta gradient G of xt, which is equal to the prox operator with constant lambda over beta of just the L1 norm evaluated at xt minus eta gradient G of xt. And now the advantage of seeing it like this is that we worked out exactly what this prox function is. So recall that this prox operator for the L1 is indeed easy. That's the motivation for this whole composite function optimization approach. Remember that, as we saw in a previous lecture, for any constant, positive constant alpha, the prox of alpha of the L1 norm evaluated at some function z, is some vector which I'll call u. And what is u? ui, the ith element, is equal to the absolute value of zi minus alpha, but the maximum of this and 0. So this is what this plus notation means, times the sine of zi. Now this is called the shrinkage operator, because basically what it does is it takes every coefficient and it shrinks it towards 0 by alpha. If it's closer to 0 than alpha, then it just moves it directly to 0. So let me just give you an example here. So if alpha is equal to 1.5 and z is equal to, say, minus 2.5, minus 0.7, 2.2, then the prox alpha of the 1 norm of z, let's see what it does. It's going to shrink towards 0 by 1.5 whenever that's possible. Minus 2.5 is farther than 1.5 from 0, so that shrinks that to minus 1. 0.07 is less than 1.5 away from 0, so that shrinks it directly to 0. And 2.2 is more than 1.5, so this shrinks it to 0.7. So we have a very simple interpretation of what proximal gradient is for our setting here, and this is exactly the ISTA algorithm. So let's see if I can squeeze this right on the bottom. So ISTA, for our function here, is this shrinkage operator. That's the prox of lambda over beta. And now you'll have to remind yourselves, what is beta? What is smoothness for this norm? I'll give you a hint. It has something to do with the eigenvalues of A transpose A. That's something for you to think about. Prox of the L1 norm of xt minus the gradient of that first smooth term, which again is just twice A transpose times AX minus Y. So in other words, you compute xt minus twice A transpose AX minus Y, and then you just shrink it to 0, just like this operation, by this factor of lambda over beta. And this gets us our order 1 over t convergence. Okay, let's finish up by moving to something even faster, the fast iterative shrinkage and thresholding algorithm. So the idea here is, as I've written on the slide, just to combine proximal method and acceleration. So this is pretty straightforward, and it goes as follows. So again, my setting is I want to minimize f of x, which is equal to g of x plus h of x. G of x is beta smooth. So what this does specifically is I need an additional sequence of scalars and also another vector that's going to allow me to build in this idea of acceleration or momentum. And I do this as follows. I'm going to set mu0 to 0, and then thereafter update mu0 as follows. Mu t is going to equal 1 plus 1 plus 4 mu t minus 1 squared. All of this divided by 2. And then I need mu t in order to allow me to define this mixture that's going to define my momentum. And that's going to be given by this constant gamma t, which is equal to 1 minus mu t divided by mu t plus 1. Okay, so I need this sequence of scalars, and I'm going to use them in the following way. X is going to be my iteration, and I'm going to initialize at some x1 equal to z1, some arbitrary initialization. And thereafter, I'm going to update x and z as follows. z I will update exactly by an ISTA step. So zt plus 1 is equal to basically exactly what we had on the previous slide. Prox 1 over beta times h, which is the same as prox of lambda over beta times the L1 norm, of xt minus 1 over beta times the gradient of g of xt. This is exactly what we had on the previous slide. And xt plus 1 will be now, you'll see this momentum term here, 1 minus gamma t times zt plus 1 plus gamma t of zt. So you'll see that xt plus 1 depends not only on xt, but it also depends on xt minus 1. That's exactly this concept of momentum. So specifically for what we had above, for lasso, this becomes zt plus 1 is equal to the prox of lambda over beta of the L1 norm, evaluated at xt minus 1 over beta times the gradient of g of xt, where this term is exactly what we wrote on the previous slide. Twice A transpose times A xt minus y. And this has convergence rate order 1 over t squared. In other words, I need 1 over square root of epsilon steps in order to have epsilon error. So these are the details for implementing ISTA and FISTA for this very important problem of sparse recovery. We're going to stop there and pick it up next time.